Okay, guys, I'm going to be lecturing on chapter 2, the chemical basis of life. Um, so let's get started. So, for this chapter, it's a really big basic review of your chemistry. So, one of the first things that we're going to be talking about is matter. So, matter refers to anything that takes up space and has mass. Make sure that you guys are not getting confused with weight. So, matter has, again, a pencil, air, your body, all have matter, they all take space. However, weight, on the other hand, can change based on gravity. So if I go to the moon, I go to another planet, right? The gravity is different. Then my weight is going to be different, but my matter, what I'm composed of, is going to be the same. So make sure you guys know the difference between those two. Uh, uh, Atoms and matter can exist as a solid, liquid, or gas. They're composed of elements. And elements, I'm not sure if you guys remember your periodic table, but it's basically those elements that cannot be broken down into any other substances. Like gold. Gold is the purest form. There's no other way that you could turn gold into uh, or break down gold any further than its basic composition by normal chemical means, right? There's always those extraordinary means that we could do. But again, that would go into the realm of atomic bombs and stuff like that. But for our purpose, for our class, make sure that you guys know that elements are basically substances that cannot be broken down any further. Uh, our body is made out of four of those elements, or it's primarily made out of four of those elements, with some other in small quantities. The most that we have that make up 96% of our body are carbon, hydrogen, oxygen, and nitrogen, or how I like to remember it's chon. For those of you who speak Spanish or are Latin, you probably understand the reference. But for those of you who don't, just know that C stands for carbon, H stands for hydrogen, O stands for oxygen, and N stands for nitrogen. So those are going to be the four main ones, four main elements that our body is made out of. However, we do have small quantities of other elements. For example, calcium, phosphorus, iron, right? Those are going to be also present in our body, not in large amounts, so not like oxygen, carbon, hydrogen. However, they are going to be present in small amounts. But even though they're in small amounts, it's still important to take note that they're very, very important in our body. For example, iron. Iron is found in a very small percentage. However, it plays a big role in our body because it's the element that allows us to basically carry oxygen in our blood. Without iron, we wouldn't be able to do that task. So just keep that in mind. So when we're talking about the periodic table, there's different types of information that is given to us. So for example, in this, we're able to see the symbol. Symbol basically shows the the abbreviation of that element. We have the complete name of the element, the atomic number, and the mass at the bottom. In atoms that are not are going to be uh, in atoms, sorry, I lost my train of thought. So in atoms, we have three different parts to them. We have neutrons, protons, and electrons. Neutrons will be neutral, and they're going to be found inside of the nucleus. Protons are positive, so P for positive, and those are also going to be found in the nucleus. And then the electrons are going to be negative, and they're going to be found surrounding the nucleus in the orbitals. So those are the three basic parts that all atoms are made out of. Make sure that you guys keep that in mind. In the next slides, we're going to be seeing how those come together. So here we have the protons. So protons are going to be symbolized with a positive sign inside. Those are found in the nucleus. Neutrons are also going to be found in the nucleus. However, those don't have a charge. And then the electrons are going to be on the outside surrounding the nucleus. And this is the model for helium. So in atomic numbers, so we have the atomic number that basically uh, classifies or orders the elements based on the number of electrons they can have on its outer rings. When we're reading a periodic table, we have periods and groups. So groups are going to be going down in columns. So I know it shows like this, right? But just keep in mind that groups are going to be going down, they're columns, and then periods are going to be in rows. So just if you ever have to read a periodic table and they're telling you go to period 3, row 5, or group 5, you guys should be able to go across, right? Period 3, column group 5, it'll be phosphorus, okay? So in case you ever have to do that, that's how you read a periodic table. So those were, again, atoms that are neutral. However, here we're starting to talk about atoms that are a little bit specialized, and these are going to be specialized types of elements that the only thing that they have different from the original type of element is going to be the number of neutrons. And we call this type of elements isotopes. So isotopes are going to be basically elements or atoms that are specialized, that are used all the time when we're talking about taking x-rays or trying to find tumors inside of a body or trying to carbon date some fossil that we found. So those isotopes are going to be very useful in that. We have here we're looking at the isotopes of carbon. So on here, carbon 12 is the original molecule of carbon. Carbon 13 and 14 are isotopes of carbon. So carbon 13 and 14, again, the only difference here comes in the number of neutrons present. So I'm not sure we talked about it or I didn't mention it, but essentially the atomic mass of elements is calculated by taking the number of protons and neutrons, adding them up, and that basically gives us the atomic mass for that molecule. In this case, we're talking about carbon 12. We give it a 12 because if we add 6 plus 6, that's 12. Carbon 13, 6 plus 7, that's 13. 6 plus 8, that's 14. So essentially the number next to it changes based on the atomic mass. And again, because the atomic mass is calculated by the protons and neutrons added together, then essentially they will have different mass numbers. But again, the protons and the electrons are all going to be staying constant. The only thing that changes in isotopes would be the number of neutrons. And again, like I said before, we use them all the time for medical purposes. Some people have used it in bad ways, right, to try to poison leaders, obviously in bombs and stuff like that, right, radioactive equipment and stuff like that. Uh, they're out there. It just depends on how we use them. That determines its utility. Arrangement of electrons in an atom. So here we're looking at how the electrons are arranged. Electrons are constantly moving. They're never just set on one stage. And they're always going to be having some sort of energy level or electron shells. The closer they are to the nucleus, the lower the energy they have. If they're farther away from the nucleus, they're going to be having more energy. For atoms up through number 20, we follow this rule of filling up the shells based on electrons. So on the first shell, on the first ring from the nucleus, it could hold up to 2 electrons. And then thereafter, the second ring, third ring, so on and so forth, can hold up to 8 electrons. So they follow basically the octave rule. The octave rule basically shows that elements are happy when all their spaces, their outer spaces for electrons are filled up with 8 electrons, or in the case of hydrogen with 2 electrons. And essentially, they're going to be doing different types of chemical properties and different reactions and combining with other elements and rearranging their electrons to be able to fulfill this octave rule, which is, again, the octave rule is going to be having most stable with 8 electrons. So they're going to be their happy place if they have all 8 electrons on their outer shell. So again, here we have hydrogen, carbon, nitrogen, oxygen, and phosphorus and sulfur. So for this type of elements, these are going to be the 6 more important elements. As we could see, here we only have 1 electron on the outer shell. Here we have two electrons on the inner shell. So on the first ring, two electrons, and then it could hold up to eight electrons on the outer ring. However, here carbon it only has six electrons. So we have one, two, three, four, five, six. So those are six electrons. Nitrogen again has seven. Oxygen is pretty stable on its own. Uh, Along with phosphorus and sulfur, they're going to be having 8, 15, 16. So again, looking up at the different electrons, they're going to be, because they don't have their all the 8 electrons uh, surrounding the ring, they're going to be really radioactive with other molecules. So they're going to always try to join or combine with other molecules or other elements to be able to uh, fulfill that octet rule. So when we're talking about molecules and elements, we need to be aware of what it means. So when we're talking about molecules, we're talking about just groups of atoms bonded together. So it could be, for example, oxygen gas, water. This is the formula for sugar, nitrogen gas. So these are all considered to be going to be considered to be molecules. It's just groups of atoms held together. When we're talking about compounds, on the other hand, compounds is always going to be atoms of different elements. So here we have hydrogen and oxygen. So that would be a compound. This is going to be carbon, hydrogen, and oxygen. That's another compound. However, if I were to give you an example in the exam of oxygen gas, O2, or nitrogen gas, N2, those two would not be considered to be compounds because it's only made out of one type of element. In this case, it will be either only made out of oxygen or only made out of nitrogen. So in order for us to consider it to be a molecule to be a compound, it needs to have two different types of elements. And now that we're talking about combining elements, we could start talking about the different types of bonds that are formed between this elements. So we have two types of bonds that we're going to be talking about here. The first one is ionic bonds, which is essentially created when we have opposite charges, with molecules of opposite charges. Covalent bonds are going to be made when the elements are going to be sharing electrons to complete their outer shell and again follow that octet rule. Ionic bond, again, we have the great example here is sodium and chlorine. Sodium and chlorine are going to be really, really good examples because each of those, if we were to draw the electrode diagram for them, sodium would has an extra electron, so it has two two electrons on its inner shell, 8 electrons in its outer shell, um, and then one extra one on the third ring. Again, that third ring only has one electron. So if we follow the octet rule, sodium, by following it, would want to be giving up that electron. So that way it only stays with two rings, the two that are filled in on the first ring and then the 8 on the outer ring. So sodium would always be giving up an electron. In chlorine's example, however, chlorine only has 7 electrons on its outer valence shell. So in order for it to complete, again, the octet rule, it's always going to be seeking to add an electron uh, to its valence shell. So these two combine together. So if sodium gives up an electron, it becomes positive. If chlorine accepts an electron, it becomes negative. And because these two now become charged, right? Sodium became positive, chlorine became negative. Now they could form an ionic bond. So because they are of opposite charges, now they get attracted to each other. So in ionic bonds, it's basically going to be created when the elements or the molecules are either gaining electrons or losing electrons. So if we remember electrons are negatively charged, we're basically going to be talking about that. So if in life you gain negative negative comments, negative friends, then your life will probably turn up to be really negative. However, if you get rid of negative stuff in your life, then you ultimately can become positive. That's essentially what's happening here. Sodium gives up an electron, chlorine gains an electron, sodium becomes positive, chlorine becomes negative. They are of opposite charges. Now they could form an ionic bond. So we have that happening here. So here's what I was talking about. In the first ring of sodium, in the first valence shell, it could hold up to 2 electrons. The second ring, the second outer shell, can hold up to 8 electrons. And then on the outer one, it could hold only one, or it could hold 8. However, it only has one. So again, sodium is going to do everything in its power to try to get rid of that 1 electron. So it could only stay with its two first valence shells. So it's going to be getting rid of that electron. Chlorine, on the other hand, has 2, 8, and then 7 electrons on its outer shell. Again, it wants to have 8 electrons to be able to follow that octet rule. So it's always going to be trying to gain that electron. So here, sodium gets rid of that electron. It loses an electron and it becomes positive. Chlorine gains an electron and it becomes negative. Because sodium and chlorine are now opposite charges, now they could form that ionic bond. So that's how ionic bonds are created. Now moving on to covalent bonds. So covalent bonds are going to be essentially atoms that are sharing electrons. So instead of becoming positive or negative, gaining electrons, losing electrons, maybe it's not just one electron that they have extra, maybe they have multiple electrons that are extra, or maybe they're not just missing one electron, they're missing multiple electrons to fulfill that octet rule. Then their better option is to form covalent bonds to share those electrons with other molecules that are also lacking electrons. So in this case, for example, we have hydrogen gas. As we looked before, hydrogen gas only has one electron on its outer shell. However, when it combines with another hydrogen gas, it shares those two electrons, and now on the first outer shell of each of those hydrogen molecules, we could consider them to have a complete shell holding up to 2 electrons on the first shell. So because they're sharing the electrons, we say that they are forming a covalent bond. So that's a single covalent bond. Again, we could also form double covalent bonds. In this case, we're seeing the example of oxygen. So again, oxygen only has 8, so 2 here and then 6 on its outer shell. In order for it to fulfill the octet rule, it's going to be sharing this 4 electrons with another oxygen molecule. So we're going to be seeing them forming 2 bonds. So basically one bond is created every time they share a pair of electrons. So because we're sharing 4 electrons, we're basically sharing 2 pairs of electrons. So we form 2 bonds, or in this case, a double covalent bond. And again, we could form different bonds, form different shapes as they covalently bind to each other. So here we have the example of carbon with 4 different hydrogens attached to it. Again, the shape can become a little bit different depending on the attachment of those hydrogens. Okay, moving on to the next concept, which is going to be looking at formulas and reactions. I'm pretty sure everybody has looked at some time in their life at different chemical reactions. So just a quick review, just make sure that you guys understand that reactants are always on the left side of the arrow, while the products are shown in the right side of the arrow. So here we have hydrogen gas combining with oxygen gas to form 2 molecules of water, or H2O. So again, we combine them. These are the reactants and these are the products. When we're talking about formulas, we also need to make sure that they're balanced. An equation is balanced if the same number of each type of atom occurs on both sides of the arrow. So here I have 6 carbon, so 6 times 1, an imaginary 1 that is here. So 6 times 1 is 6 carbon molecules. So when we go to the other side on the products, we need to make sure that whatever is showing here is showing that it also has 6 carbon. Same thing with oxygen. Here we have oxygen times 6 times 2, that's 12. 12 oxygen plus another 6 of that water molecule. So again, we need to make sure that we are getting those oxygens accounted for as well, which we do. Same thing with hydrogen. 6 times 12. 6 times 2 is 12. Again, here we see the hydrogen, there's 12. Again, this equation is a balanced equation. And by the way, this is the equation for photosynthesis. So now moving on to basically the important part of this chapter, which is looking at water. Water is of severe importance to life. Life began in water, and basically the single most important molecule on Earth is water. All organisms are made out of 70 to 90% water, so obviously it's super, super important. Water has unique properties that make it a life supporting substance. So when scientists and astronauts are looking at other planets, like Mars or different planets, right? Right now, the one that we're most interested is going to be Mars. Scientists have found that there's water, that there was frozen water on Mars, and they get super excited because of that. Because again, life began on water, so water is essential in order for life to take place. So if there's a planet that potentially has water that is useful, then there's probably going to be life as well. So again, that is why again scientists get excited when they see water in other planets. Water molecules, one of the important properties of water and why it's so important is because water can form polar covalent bonds. So we talked about covalent bonds, saying that covalent bonds is when molecules or compounds are sharing electrons. Here we're seeing the example of water and other, in this case, in other elements that are also sharing those electrons. However, they are sharing them unequally. So here, the chlorine, they're sharing their electrons equally. They're both equally getting those electrons. This one, the polar covalent bond, on the other hand, if we were to combine chlorine and hydrogen, chlorine would want to keep the electrons more towards its side. The best example and the best way that I could explain this is if you give two kids a box of colors. You give the two kids a box of colors, they're sharing the color box, they're sharing all the colors. However, one kid ends up getting the colors more towards their side, more towards their desk. So again, they're still sharing those electrons or they're still sharing those colors, crayons, but one is going to be having them more towards their side. And that's essentially what happens here. Whenever that happens, we are saying that this is going to be forming some electronegativity. So chlorine is going to become, because it's gaining more of the electrons towards its side, it's going to be gaining a slightly negative uh, electronegativity, while hydrogen is going to be having a slightly positive uh, electronegativity. And essentially, that's how polar covalent bonds are found, are created. So hydrogen bonds is the last bond that we're going to be talking about in this chapter. Hydrogen bonds are created when water molecules or other polar molecules are going to be interacting with each other. So let me see if I see. Okay, so oxygen in this case would be slightly negative. Hydrogen will be slightly positive. So sort of like we were talking about in the ionic bonds, and the charges are going to be attracting each other, or opposite charges are going to be attracting each other. Same thing is going to be happening here. The slightly positive hydrogen from this water molecule is going to be attracted to this slightly negatively charged oxygen, forming a bond called the hydrogen bond. So hydrogen bond again is slightly negative oxygen in another water molecule. So they're forming those bonds between them. So here are the 6 different properties of water, which basically make water be very, very important. In the next slide, we're going to be talking about those properties in a little bit more detail. So the first property that we're seeing of water and why water is super important is because water is a good solvent. So if we think about when we're making lemonade, for example, we put water, we put sugar, we mix it really well, and the sugar dissolves, right? That is essentially what water is, in this case, in this slide, it's talking about water is a really good solvent. It's going to be able to break apart those bonds between ionic molecules. Um, and it also is going to be organizing the molecules a little bit better. So when we're talking about water molecules interacting with other molecules, we need to be aware of these two concepts, hydrophilic and hydrophobic. In the next chapter, we're going to be talking about these two properties a little bit more. But essentially, a hydrophilic molecule is going to be highly attracted to water. A hydrophobic molecule, phobic meaning fear, hydro meaning water, so it's going to have a fear of water. So molecules are not going to be attracted to water. So when we're talking about water as a good solvent, a really good example is going to be NaCl. NaCl, for those of you who don't know, is your normal table salt, right? It's just salt. So if we were to mix salt with water, again, we mix it really well. Uh, it basically breaks apart the crystals of salt, and that is essentially what happens. The ionic bonds are broken, and therefore it dissolves in the water. Water is going to be having these properties of cohesion and adhesion. So when we're talking about cohesion, this is when water is binding with other water molecules due to hydrogen bonding. In adhesion, however, we have water having the ability to cling to other polar surfaces. So it doesn't have to be other water molecules, it could be just another polar surface. So cohesion, water with water, uh, and then adhesion is water with polar molecules. And this is essentially what allows plants to be able to move water, transport water from the roots all the way to the leaves. So if you've ever asked yourselves, how do the leaves of a really, really tall pine tree get their water from if we are only watering the base or the roots? It's essentially because of these two properties, cohesion and adhesion. So here we have the example of water sticking with other water molecules. Again, that is going to be known as cohesion. And then by the same hand, we have water molecules sticking to polar molecules. In this case, the polar molecule would be the tissue of the actual tree, the walls of the tree. So the walls of the trees are polar, so the water is going to be sticking to that polar wall. So if we were to think about the water moving from the roots all the way up to the leaves to the branches, it's basically forming that little zigzag line to be able to transport it. We also see it in us, for example. We have water being transported in our blood vessels. Water sticks with the water molecules, but then they also stick to the blood vessels, the walls of the blood vessels that are polar. So again, cohesion and adhesion. It also, water has a really high surface tension. So here we have an example of an insect that is able to walk on water, known as water striders. Because water has such a high surface tension, the water molecules are basically clinging to each other really, 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 really tightly, more tightly to each other than the air that the water strider is able to actually emit to the water. So it's basically like if we were saying that the water strider is a little bit lighter or it's a little bit less weak in terms of force. So it doesn't have so much force that it's able to disturb those hydrogen bonds or that tension between the water molecules. So it's basically like if it was walking on solid ground. The other properties of water is that water has a high heat of capacity. High heat of capacity is basically that water temperature rises and falls slowly. So if we think about going to spring break, right? Spring break is usually in March. We just went over winter. We're sort of entering spring, but it's not there yet, right? At least here in South Padre Island, if we were to go on spring break and try to get on uh, the water is going to be very cold, right? You're like, oh my God, like the sand is hot, like what's going on, right? Shouldn't the water also be cold or should it also be hot? Well, because water has high heat of capacity, it's able to resist a lot of that heat. So even though the sun is beating at it, It takes a lot of energy for that water to rise at least 1 degree Celsius. So uh, technically the water, at least here in South Padre Island, wouldn't be able to be ideally warm until we get until July, August. That's when the warm temperatures come in. And because the sun has been hitting it constantly, like every day for the past 3 or 4 months. The next property again is the heat of evaporation. So it takes a lot of energy again to break those hydrogen bonds in order for that oxygen and those hydrogen bonds to be broken apart into gas, right? So heat is dispelled as water evaporates. If you think about leaving a water bottle on your car, right? It could be 110 degrees outside, but the water inside of that water bottle doesn't immediately evaporate, right? And that's because again, it does take a lot of energy in order for that those bonds to break apart. So it doesn't evaporate as easily. So again, those are going to be important when we're talking about boiling water. If you go outside, you're running in the hot heat. Again, you're not going to become super dehydrated really fast because again, it does take a long time for that water to evaporate from your body. And when it does, then obviously you have to rehydrate. Another property of water is that water has varying density depending on its state. So, as a liquid, water has high density. As a solid, it has a lower density. And it all has to do with how the molecules of water arrange in these two different states. So, in the solid form, the water molecules form sort of like this hexagons that essentially have a lot of spaces in between, a lot of air in between. They expand and they freeze. In a liquid form, the water molecules are more tightly together, therefore, they become like a little bit heavier. So, if we were to think about it, think about obviously up north in like places that it actually freezes, Michigan, stuff like that. The water in the ponds and in the lakes freeze, but the water in the bottom is still running, right? So ice essentially acts as an insulator for things like fish and other stuff to continue living throughout the winter time. So in movies, they usually show the people in the ice picking at it and then putting a fish rod going down that hole. Again, why? Because there is fish living under the ice cap, and they're alive because again, that ice that is forming on top is going to be forming as an insulator for them, so that the water below doesn't get as cold. And then the last part will be that water dissociates into equal number of hydrogen ions and hydroxide ions. So here we have the molecule of water, so HO2, right? So HO2 or H2O, H2O, sorry. So we have two hydrogen, one oxygen. This can break apart, so we form the hydrogen ion and the hydroxide ions. So this is going to be coming into play when we're talking about acid and bases. So okay, so in acids and bases, when we're talking about acid and bases, we're basically talking about the concentration of hydrogen ions. So we're seeing how much hydrogen ions does the molecule have. If it has a lot of hydrogen ions, then it's going to be acidic. So for example, lemon juice, vinegar, coffee are all going to be having high numbers of hydrogen ions. Therefore, they're going to be considered to be acidic. So things that have low amounts of hydrogen ions are considered to be basic. So things like milk of magnesia, ammonia, those are just a few examples of, of chemicals that are going to be basic due to the lack of hydrogen ions. So if we were to put it on a pH scale, pH below 7, so 0, 1, 2, 3, 4, is considered to be acidic. A pH above 7 is considered to be basic, so 8, 9, 10, 11, 12, 13, 14. All those we consider to be basic, and pH of 7, just 7, flat out 7, is considered to be neutral. So we have equal numbers of hydrogen and hydroxide ions. in a solution that has more hydroxide ions than hydrogen ions than hydroxide ions, it's going to be acidic. Again, if it has less, then it's going to be basic. So here we have a scale. In your exam, you might see a question about lemon juice has a pH of 7. Lemon juice is considered to be what? An acid, base, neutral, uh, none of the above, right? You should be able to tell me, okay, lemon juice has a pH of 4. Then if it has a pH 4, then it's going to be considered to be acidic. If I were to tell you ammonia has a pH of 10, what would be what would it be classified under? And it'll be considered to be a base. So make sure that you guys keep that in mind. Make sure you guys know that because it will be on your exam. And then the last part that we get to is buffers and pH. So how do they go together? How do they relate? Essentially, chemicals or combination of chemicals that keep the pH within normal limits. So what a buffer does is basically it doesn't matter how much hydrogen ions you add to a solution, it will not become too acidic. So even if you add a lot of acid solutions to it, it would still be considered to be a little bit within the range. So, for example, the pH of blood is 7.35 to 7.45, and because it has that buffer, the blood basically stays within that range. So, if you were, for example, to drink alcohol or stuff like that, you increase alcohol is acidic. If you increase the pH of the blood, then because acidic, then we get diseases like acidosis. This is essentially just a high amount of acid in your blood. And if that happens, obviously your blood is not going to be able to transport the oxygen like it's supposed to do. And obviously that is not good. So again, make sure that you don't drink too much alcohol, right? Because then again, it can happen. And that's why alcohol poisoning is really, really bad. So hopefully you guys, again, if I went too fast, you guys could go back and hopefully rewind and go back to the parts that you guys didn't understand. Hope that really helped for you guys. Again, chapter one, I didn't post a video just because I want for you guys to be able to learn how to study on your own because maybe my lectures are not good enough. But if you ever, again, can't get to through all the video, then you guys can study on your own and read on your own. So I just wanted to give you guys that option for week one. For the following weeks, I'm going to be trying to be posting regularly the chapters reviews or my chapter lectures. So thank you.